So now we are in the same unit 2, geotextiles. We are going to talk of now the actual design of geosynthetic reinforced soil structures by one of the most popular methods. So this is, we call it as basically B.S. method. What we mean is that it is a method developed by the British Standards Institution, BSI. We should not get confused with the Indian codes, because India, we call it as Bureau of Indian Standards. It is BIS. Here it is BSI. So to avoid confusion, in our codes we call IS codes. We don't say BIS codes, so that no confusion. In the British codes, we always call them BS code actually. Okay, anything BS means British standards usually. Okay, now we find that it's very BS 8006 is the number of codes, and then the first code of practice has come in 1995. It is revised in 2010 and further revised in 2016 also. So what we feel is that it is being continuously modified to suit experiences. Then we should get used to the words code of practice, COP. Also, this is a very peculiar name, code of practice for strengthened and reinforced soils and other fields. It doesn't say for walls, it doesn't say for slopes, it doesn't say vessel enforcement, it says only for strengthened or reinforced soils and other fields. So that is very important. Britishers are very strange people, but anyway, that is the code we are going to look into. Now, before this code has come, actually, there was a document in UK only. It was called as BE 3/78. That means code, you can say manual or guidelines. In 78, it was evolved basically. Now, barring that, before that, there was no other code of practice. When we started work in this in 1985, we had only methods developed by the manufacturers, possibly based upon that British memorandum BE 3/78, and that emerged ultimately into the British BS 8006. Is the, we can say, is almost like the very first document which has come in such great detail basically, and it is what we follow from beginning to end. Basically, it is almost, it reads like a textbook. Doesn't read like normal codes, because several things are de novo, and also there are several approaches which they have included in the entire thing, and we'll see what exactly things now. The other things which I also come to know later, not in this particular series, I mean not in this particular design methodology which are starting now, is what we call as the method given by the Federal Highway Administration and through the NHAI. I will tell you what are these things actually. What is FHWA and what is NHAI? And in India also we have got one in 2014, guidelines for design and construction of reinforced soil walls. Okay, design and construction of another word here we are finding is design and construction of mechanically stabilized earth walls. In the US now, whatever we are calling as reinforced soil walls, just reinforced soil walls are called as MSC walls, mechanically stabilized earth walls. That's the terminology which we understanding it, but in India we use reinforced soil walls or reinforced soil structures or reinforced soil slopes. Okay, in this, before we go ahead, we should understand a certain terminology now. The first terminology is that any standards institution issues 3 different kind of documents. One could be a code of practice or guidelines or manual. The second way of angle is method of test, and third is specification. Okay, that's why we covered methods of test earlier in the previous classes. Okay, before the principles of reinforcement are taught now. And then before we develop a code of practice is mandatory. That means you have to follow each and every word, each and every letter, each and every clause you have to follow very systematically. That's why it is 100% mandatory. Guidelines are just giving you obviously guidelines only. That means there is room for some maneuvering here and there. Sometimes manual is a better word than that. That means maybe from guidelines, you move on to manual and then go to code of practice. Okay, in this code of practice now, we are obviously having the parameters we said already earlier. It could be flow characteristics, it could be what we call as friction characteristics, or it could be strength characteristics. So all of them have defined them are given by the methods of test for each of the materials, whether soil or rock or geosynthetics or concrete, everything is given method of test actually. Then for our own use now, for our own use basically, we have what we call as a specification. That's what we said. when we are going to finally evolve a particular product now, we have to be not only seeing the design method, design parameters, but also the insertion damage. We are going to talk of the durability and many things we are going to do, and also some factors will be there. So all of them are given as a specification. So method of test, specification, and code of practice together form one set actually always. Okay. So here we are referring to code of practice, which is obviously evolved from the earlier guidelines against and manuals, and then came into code of practice. We'll see again in what way the British method is what do you call very specific in certain issues. Then in India we have this Indian Roads Congress. Indian Roads Congress issues obviously with the numbering also you can find out. For example, we have IRC 37. IRC 37, that means the number IRC 37. Let's say 2019, IRC number 37 means it is a mandatory. That number, just number means mandatory, and it always gives the year of reference. Then there is IRC SP 59, that means special publication. 59 for meant for payments. No, that is only giving a guideline or manual. That means it is not necessarily mandatory. It gives you an assistance basically, and then we can sometimes diverge also from that now. But as 37 payment design is what you call very clearly mandatory. In the same way, when we have a contract in India, it is guided by the specifications book of specifications for roads and bridges. Let us say in this case by the Ministry of Road Transport and Highways now. So that is specification book now. That means everything which are going to be in the country, all contracts, road contracts are all governed by the specifications book. It's a huge book actually, almost 1,000 pages of the ministry. And then we have, of course, the Bureau of Indian Standards, very similar to British standards. We have something from that. And also we have, obviously, the ISO. And sometimes before ISO, it comes to ISO, there's also European Union, which was giving them. So either European Union or ISO. Normally it is slash, or finally this emerges into ISO also. That is International Standard Organization. Okay. That's why we're trying to do that now. Now, when once we said that there is also an American method now, obviously, in America, the practice is slightly different now. You must have heard of words ASTRO. What is ASTRO? Anybody knows? What is ASTRO? ASTRO really means that American Association of State Highway and Transportation Officials. Okay, State Highway and Transportation Officials. That means they also deal not only with roads, also with other structures, airports. Also, they deal with even ports and harbors. So they deal with now. So that is organization officials now. Usually, they meet and give out some documents, let us say. In fact, they don't bring out themselves, they appoint a consulting organization who are the real experts. It could be a professor, it could be an consulting organization, approved organizations from them. And so they give that award the work to them, get it from them under their guidance. And then, of course, they have their comments on that now, modified now, submit to the government now, because ASTRO is a private body. And they submit to FHWA, that means Federal Highway Administration. And FHWA approves that finally. Okay, so that means the documents which are seeing in America, particularly in our area, is ASTRO, FHWA. Okay, combined together now, they have another system called NHAI, National Highway Institute, which basically propagates. It also brings out document now, combining both ASTRO and FHWA. So for our reference now, we say that ASTRO and FHWA, but always refer to the documents given by NHAI. The documents are done by NHAI, they propagate also through a lot of shortcuts and things like that now. And what is method of testing in America? It is ASTM, American Society of Testing Materials. Mind you, even this is not really a government body. It is a American Society for Testing Materials, but today it became a standards body. Okay, that is one thing is there. They also refer to ISO anyway. Okay, then in the methodology which are going to follow for actual design, obviously in the present NHAI document, not present, just because this one is revised recently, whatever corresponding to our own work now is revised more recently. In fact, we don't have a formal copy of that a few months back. But till then, it was only a method which we call as LRFD. That means load resistance factor design method. So when you go through this method now, naturally, the NHAI method refers to this kind of system. In normal designs which you are going to do anywhere in electrical engineering, he is referring to ASD method. That means there is a applied stress or applied strength design method now. So for us, what it means is that these are actually giving a more or less now a kind of global factor of safety. That means, okay, this is factor of safety. For example, we do a slope stability design now. So they say that, okay, the factor safety is 1.3. They're not going to say anything more than that. They're not going to say how the loading is done, how the resistance is done. They will not say anything at all. So just based upon the total magnitude, say that, okay, this is the global means all parameters included. That is the main thing now. And before that, also it was there, but then the limit state method has become more common now. So our code of practices are going to cover the BS 806 following the limit state method now. In the limit state method, obviously, we have a lot of parameters which are called as partial factor of safety. There is also a overall factor of safety. So you understood the differences between these different codes now, Prabhakar?
Yes, sir.
Okay. And the difference between ASTO and FHWA. So the Federal Administration provides stewardship over the construction, maintenance, and preservation of the nation's highways, bridges, and tunnels. So what is important is that apart from just giving the designs philosophy only, they are also equally bothered about the construction and the maintenance. Okay, these are very important because they have manuals clearly to say that you have to do this and this and this, or after 50 years you have to construct a bridge, or whatever it is, they are able to maintain the bridges, or of course reconstruct if required. And it also does research R&D and provides assistance to state and local agencies to improve safety, mobility, and to encourage innovation, which is very important now. This year's identification they have done is one is safety, infrastructure, innovation, accountability. So every year or every 1 or 2 years now, they give a focus on certain aspects now. I'm not going to get into those things now, but safety, infra, and innovation, accountability is very important. And please remember that not all the roads in America are very good. Don't expect that everything is best. They try to improve them within the limitations which they have also got. And what we are going to refer to later, particularly when we go to the design of our structures with geogrids now, is, as I mentioned, the documents brought out by the National Highway Institute. Now, this is the, as I mentioned, the training and education arm of the federal administration. That means they bring out documents and also do a lot of courses and obviously training and education on very many aspects actually. So this is the structure they've got now, important structure we should understand. So from the British Standard Code now, we are going to refer initially, of course, the first edition itself, that is 1994, and then see what more changes occurred up till 2016. They may not be so relevant to you, but the very fact that it is divided into 8 or 9, you can say, aspects are fundamentals of soil reinforcement mechanism, applications of soil reinforced structures, reinforced soil walls, limit state philosophy, partial safety factors and load combinations, minimum geometry requirements, design methodology and checks, detailing specifications. Actually, it reads like a book. It's very interesting for you to read. It's easy to read also. So, in fact, this sketch I used in the last class is exactly taken out from the code. Very rarely, the code gives you the philosophy of all of them now. So, in this case, I just want to show you also one of the earliest data which is available on sand, let us say, same contractual system now, and traction system, and very small confinement, I think it's only 5 kPa. And they did the traction test, and this is the result on that sand. Okay, so this is the strain, and this is the maximum principal stress. Okay, and then these are in kilograms per square units. So what is it you find is that they mix this same sand now with the wood shavings. You know, the carpenter, when he's leveling any what called beam or something like that, he got that wood shavings, you know, very different shape, kind of curved shape they have got. So from that fir wood now, if it is the inches now, 0.008 by 0.05 by 1 to 3 inches, they can say how fine they are. He just added only, this is Lee, long back, Lee is no more, Lee is no more. He just added 1.2% by weight of this kind of wood shavings, wood waste, you can say that now. And out comes actually this behavior now. This is the beginning of our work basically. What work we have done? We found that if you think that there's a limit on this maximum value, so naturally all these values we are getting by so-called such reinforcement, you know, this strength actually increasing by 5 to 6 times. You know, here we 0.2 and this is about 1.2 kilograms centimeter square. So you can imagine how much strength is improving. We also see in the slopes are indicating a higher modulus, and then we see that it is already coming to residual state kind of thing. Here it is still almost near the peak only. So these 3 points have come out by this kind of waste also. Then the other result from one of our students now, Ivana Sand and Owen Geotextiles, those are called 501. I have shown this picture to you again because of these things, because this gives you more detail of, we had a specimen which is tested at 0.5 kilograms centimeter square, that means 50 kilopascals. And with one reinforcement, with one reinforcement, this is the picture. And then with two reinforcement, this is the picture now. Single disc and double disc actually. So you see this now, the first curve, the black one only is here. And from here, just adding one disc has changed the strength. You can almost say 80-90% increase in strength. And then we find that further increase in strength is there with respect to two discs actually, double disc. And like what I told you is, the peak is always even larger than the residual value of the unreinforced specimen. Even here also the peak is much larger. Even the residual value also is much larger actually. So you find again the modulus values are also increasing now. And the point I had to make also at the time was, when you apply higher confinement pressure, 800 kilopascals, you find difference is not much now. The difference is really not much. Whereas here the difference is going to be very significant in terms of magnitude, you can say that now. So again, as we keep moving up now, it shows the behavior. The voluntary behavior also shows it like a dense sand actually. It may be loose sand, but on reinforcement it becomes like a dense sand. Okay, that is something I thought I will just recap now. This picture also you have seen in a different way. Reinforcement can be a strip or sheet, or can be mesh, or can be anchor, or can be a rod. Different kind of systems are there. So now what they also say clearly is the range of applications of reinforced soil now. This is very important for us to recognize that initially we can think of a wall. That means a near vertical wall. We'll define that also, near vertical wall. And then an abutment is something wherein our deck slab is going to rest with a seating on the wall itself actually. So that is called abutment. And you're able to see that also the bridge deck is not resting on separate abutment. It's not resting on separate pier. It's not resting on separate pier. So that is something we have to always remember. So when you try to look at that now, so this bridge deck is directly resting on along with the seating arrangement on the so-called abutment now, and it's not resting on another pier. Like in India, we'll see that also. Then we have slope. These are all called walls and abutment. And then we have a slope, which is built from the beginning. And also we can build shallow and naturally, steep and shallow kind of thing. And this could be also reinstatement of failed slopes also. So that means failed slopes in the hilly regions, it may happen. And then even soil nailing, wherein we are going to start reinforcing. As we keep cutting down, we start reinforcing, but these are different kind of materials, nailing. But in this case, here we are constructing from bottom to top now. Everything is from bottom to top. Here what we are doing, we are putting the reinforcement. As you keep cutting, we introduce a rod or whatever it is. It's called a nail. It's not such a small nail. It's very long in length and large diameter. And we keep doing it as we keep going down. We keep applying more and more as we keep cutting actually. So that is what we call a soil nailing. And the reinstatement of failed slopes, and then a steep slope actually. Then when you consider embankment on soft soil, obviously we are going to think of this kind of system, and we reinforce it here basically. And then we can also think of basal mattress when you got a thin soft layer, and in this case we are putting reinforcement naturally, not naturally the interface, we are putting in the embankment itself actually. And we can also place them what we call a piled embankment with basal reinforcement. That means whenever we are going, I'm going to show some cases also wherein the soil is very soft now. We could have constructed on piles only, but piles are very expensive. But if we are going to use a pile solution, naturally, if you are going to have piling as a foundation for the entire embankment, which could be running into anywhere up to 500, 600 meters, now it is very expensive. So if you are going to have the piles far away, what is going to happen now? If you are going to have piles far away, naturally the pile cap is going to be large now. If you are going to have piles nearby, the more number of piles are going to come now. So as a wire media now, we can cover up these entire pile caps by using a reinforcement. So this is actually called piled embankment with basal reinforcement. This is basal reinforcement, and then below that is piling also. And then there are also sometimes cavities within the formations, and it could be coming out because of limestone and many things now. So even those cavities it will cover now. And one important aspect I wanted to show you very clearly, you should not forget this actually. This is showing a building foundation, and what it says, this is just a kind of a shed or godown or something like that now, and one can think of placing a reinforcement here now. Now, what they say is that there is not enough experience with this application to be included in the code of practice. So this is not recommended by this code, obviously. And we'll also know tomorrow when we keep going further now, what is it we are going to do? We are going to look at bearing capacity improvement, not foundation improvement, because placement of reinforcement is not going to change the by and large in a major way. The settlement. Settlement is still be there. Okay, it may vary. It may be less uneven and things like this. Different settlement could be less, but total settlement is definitely going to be there. So this is what we have to really think of it now. So these are the overall general applications of reinforced soil systems, and then we can also think of definitions because let us not assume that a typical case which is shown here is all of them are going to have same length of reinforcement. All of them are going to have same spacing also. No, this is a simple wall actually. Okay, this is called a stepped wall. That means the bottom reinforcement is going to be longer than the top reinforcement. Another case, stepped wall. In particularly when you construct in hill areas now, there may not be enough space for us to construct full length of the reinforcement. So this is called a trapezoidal wall. We'll do today. We do what we call showed walls. We'll see that also. Then a full height wall. Full height wall means the entire fascia is essentially vertical, near vertical. Okay, we can also have, of course, full height panel also. That means one panel, single panel, but it's a full height wall. And in this case, a part height wall. That means wall is constructed up to it's half the height now, and afterwards we are going to have slope only. It's called part height wall now. And then a dam. That means wherever we are going to retain the water here now, on the other side we are going to put reinforcement and start doing it. We also done for increase the life of the dam also. Then embedded wall really means that on both sides we got the wall anyway. That is what is there. But the carriageway is not sufficient to have full length of the reinforcement required now. So here the kind of overlap is there. That's called embedded wall now. And then normally when the wall height is going to be more and it's difficult for us to construct large heights now, we do tiers. That means you can say this tier is resting on the bottom tier now. So 2 tier, 3 tiers are also very common now. Then an infinite slope, naturally, there is a slope here on that also. Part of hill slope retention, we can do infinite slope. And then noise barrier also is done. There are different kind of also noise barrier also. That means there's a highway here now, a high-speed highway is there, or a tram or whatever is there now. A lot of noise is not encouraged by the residents on this side now. So for them, it looks like a kind of forest or hills only, or a park. On this side, naturally, a vertical face is there, and this is a different kind of reinforcement because nothing is going to move over that now. It's only this kind of normal retaining wall now. Then back-to-back wall is very common. Particularly in almost all bridge approaches today, we have this system. That means we have one wall this side and the wall this side. So they could be same height. For example, if you are going to have different camber, probably the heights also could be different now. If the soil is different slightly, naturally the depth could be different now. But it is back-to-back wall. That means this side also wall and this side also wall now. Okay, this is what I told in the previous sketch now, wherein we are going to have directly abutment. The bridge deck is going to rest on the abutment. The other case is when, of course, like we have been doing commonly, that the bridge deck actually rests on a bridge pier basically. Okay, and this is the wall now. That means in plan it looks like as though we are approaching. So both sides are wall now near the abutment now. So this is what we call as closure wall. This is what we call as closure wall now. So approaching this, it looks like this, back to back. And when it's coming near the abutment pier now, it is called closure wall actually. Okay, and as a transition now, the traffic which is going to come through this kind of wall actually is going to be carried onto an approach slab actually. So approach slab is concrete slab resting on this only, and finally it meets the bridge deck actually. So we have designs for each one of them now. They are not necessarily different, but you start working from one to the other one now, step by step. You start with naturally walls and go to abutments also. So as I mentioned, the three kind of facings which are normally there could be the discrete panel, individual panels now, or we can have full height panels. That means single panel from top to bottom now. Easy to look at now. And then we can have a different kind of fascia. As I said, it could be the block facing. This they had it in the latest edition actually. So this could be block fascia. It could be gap band fascia. It could be back fascia. All those things could be there. And the last case is one which is called as wraparound. I have shown pictures of this also, wherein when we start constructing, we have reinforcement here now, and it's actually tucked back into this now. There is no other fascia. This itself is exposed basically. The geosynthetic is exposed actually to nature. Now, what is the advantage of this is actually there is no concrete fascia in this case now because directly this curved portion is exposed now. So, advantage of this is that as we keep constructing now, the soil is going to settle, the fill material is going to settle. So, it doesn't matter to us now because this will become whatever is curvature now, it will become more, you can say closer curvature actually, more curved it becomes now. So, that's called concertina. So, this is called also concertina wall, wraparound wall, or tie back wall. All these things are really, all the names are very similar actually. So, we have discrete panels or we have segmental block fascia. Not very common, but they're very good. Full head panels are also wrap around, tuck back kind of walls also. So these are the basic types now. When you start looking at them now, what is it we find? There are many factors which are influencing performance now. That is recognized by this code. So in this case now, what is it we are going to do? We are talking of reinforcement, the composition of that, the durability of that, the form of reinforcement, is it strip or grid or whatever it is now, the surface properties, the dimensions, the strength, stiffness, creep, and where they're located and the spacing, orientation, all of them are going to influence the overall behavior. And then soil also, particle size and shape, grading, index properties, mineral content, durability. It could be densified. What is state of stress now? Is the degree of saturation is there or not? Drainage is there or not? So all these things are going to influence our wall actually. That is something very important. And also the construction type. Construction system, compaction, handling, overall geometry, end use, and then foundation conditions. So the variety of these designs, variety of the structures make actually very interesting and also complex for everybody to follow. And we find that these are the areas about soil mechanics, basic principles of soil mechanics. So one should be very thorough with this now. And then we should also familiar with the construction, how we are going to construction, elements of construction, and as it further goes on, is it going to settle, is it going to move, is it going to distress, and then of course varieties of reinforcement now. We have already seen that there could be geotextiles, there could be geogrids, there could be strips, there could be metal, and there could be composites. So each one of them we have to pick up in a different way. So there is a certain thing which we call experience or choice by which you are going to pick up this and also pick up the soils wherever it's possible. We'll see that what do you mean by picking up the soil. So for this now, even for reinforcement, we have seen some of them, we'll see some more later. We are worried about the physical and mechanical properties of the material, its durability, performance during installation and use. Okay, what is the effect of combination of load and chemical environment and construction damage? Then details. Detail means how to connect it to the fascia elements now. Then what is the quality control procedures and production process? Pre-construction exposure to an aggressive environment. Effect of static fatigue. Effect of blast, fires, vandalism. So the point we're trying to say is that the code actually deals with all of them. It's not the list which is given an examination. All these points are taken care of in the material choice, in fixing up the what you call factor of safety, and many things are there during the course of this. We will also deal with them now. So what we have seen in the earlier long slide was, of course, that we got two different materials now which are considering. That means both metallic and non-metallic. Non-metallic I meant polymeric now. So mind you, this code is common for polymeric materials also and metallic materials, by which now naturally the steel is a basic material, stainless steel. Sorry, mild steel. Okay, so that is the main thing which we are going to look at now. So in which case, what is it we are going to follow is that for metals naturally loading, water, damage, temperature, all of them are going to be controlling. In our case, same loading, but water is not going to damage really. Here, water is going to corrode the metals actually. Damage during construction, exposure is going to damage now. The temperature is going to become soften actually. Here, temperature is going to increase obviously the corrosion now. And specifically, if you are trying to use the metallic components, there's something called electrochemical composition of the soil now. That's very important for us now. It's not so critical bacterial composition. If you are going to use natural material, this is not going to be done at all. And by and large, we have seen that if you are going to construct in normal soils, which is pH essentially 7 and 8, there is no damage to the polymer itself. But if you are constructing in harsh environments like landfills, Very rarely on sea beaches and things like that, which are already polluted, this may become considered. But here, in metallic reinforcement, they will become very critical actually. So we have to do special kind of testing for that now. The other kind of thing which I mentioned already in the last class itself is, you just imagine that this is a wedge in our wall itself or in our slope now. So in this wedge, we said there's active zone which is trying to come out, and this is the passive zone, resistance zone now. So if you are placing reinforcement here now, if this entire wedge is going to move out, what's going to happen now? This will be pulled out. Or if the pullout is sufficient length, basically, it may break also. That is our concept now. So we are bothered about the tension along the plane. We are bothered about tension along the plane, or a maximum tension which is going to occur at the junction between the active and passive zones. Okay. And then, so there is a minimum requirement for this now, based upon many things now. Whereas if you got a very stiff material as reinforcement, like let's say a rod also is reinforcement now, in which case the stiffness of the rod is going to come to picture now. So that means the shear also is going to be coming out in favor now. Now that means when we are going to use a nail, which is a rigid body basically placed in the soil now, it may also start bending or shearing, and that gives us enough resistance more than that of a normal geosynthetic or normal metal reinforcement. And that is why we will find that the length of the nails, if you are going to use the principle, is going to be generally shorter than what we have for normal geosynthetic or metal reinforcement. That is what, but remember now. So the stiff reinforcement is going to bend like this, or it's a possible bending or shear is going to happen. So we'll take advantage of that in that case now. That is the one thing we have to remember now. Otherwise, principle is same. So what else we are going to talk of? We said that this particular code of practice based upon limit state. Limit state we have not been using normally, but then I think in principle we understand it now. So what is the limit state? We'll say the limit state is reached when one of the following occurs. That means ultimate limit state, or collapse or major damage. That means the whole wall is collapsing. Okay, that is ultimate limit state. The other limit is going to be that deformation is going to be excess. That means settlement is going to be much more. The wall itself looks intact now, but is settling more and more actually. So that is called serviceability. So basically what you mean is that a collapse or major damage is going to occur because of the strength portion, and here the whole wall is going to settle. Essentially settlement may not be much in the wall itself, but settlement is also more because of the subsoil conditions. So you want to describe more of this now. The ultimate limit state which we are considering is collapse or other forms of structural failure. The specific mode of failure occurring when disturbing design effects equal or exceed restoring design effects. So for this we are providing margin safety against attaining the limit state considered or provided by the use of partial metal factors, partial load factors, partial resistance factors. So you see all of them now. The materials which are going to use, the soil, and of course the geosynthetics now, we are going to have partial metal factor safety, and the loads which are going to be there, static load, seismic load, any other UDL, concentrated load, all of them are going to be having some partial load factors, and then also we are going to have partial resistance factors. That means resistance to further movement now. So what is it we are going to really is the nominal loads which are going to have, which will calculate like our live load and static load, everything else, are going to be increased by multiplying a prescribed load factor. These factors are obviously going to be more than one. So the design load which you are going to have will be more than the actual load is going to appear there. Mind you, nominal load is a load which is calculated to be coming on the structure. And then this is increased by a factor more than one, such that we are going to have a design load. Design load is the one for which you are going to design. So increase is done by using a prescribed load factor now. In the same way, general resistance is given by soil itself to begin, or friction, let us say. So in this case now, the material properties we are going to have reinforcement capacity is going to be made safe actually by dividing by the material factor safety. So that is the design material properties. So I mentioned earlier also, we have to evolve actually in the geosynthetic case now a long-term design strength. So long-term design strength means we have to take creep also into account, we have to take damage into account. What are factors you think which are going to occur during construction and during its life of the structure? So all of them are going to be considered individually. Okay, so that is what is going to be there. These are the material factors of safety, and then finally we will get a design material properties. Then resistance. Resistance, naturally we said resistance is coming through friction only. So friction also we are going to have interaction factors again, or bearing capacity also resistance only. So those factors are also resistance factors. Again, we are going to change this by resistance factors. So we got now for each item a material factor of safety or a load factor or a partial resistance factor. So these are all partial factor of safety, you can say very broadly. Then when you come to serviceability limit state now, we are talking of two things now. One could be the vertical settlement, as usual, like in a foundation. Also, the wall could move laterally also. So that means we are talking of horizontal movement as a vertical movement now. So we have to put limits on both the things for this structure to behave correctly. Okay. Now we are able to visualize certain things now. That means we know that certain movement is must. That's what I told at the end of the last class. That movement is a must now. So construction tolerances are given actually subject to separate limits and are considered separately from any such limits. That means whatever is happening during construction is allowed. Like we said, pure sand settlement is going to occur. We are not worried about that now. Okay, so they are not considered in the settlement. That means whatever occurs, the settlement or the movement of the or the strain occurring in the reinforcement is during the construction stage is not considered. Whatever is occurring beyond that construction is only what is considered. So we should remember this also. Let's keep going now. So then for this now, for the service life, many things are there, which you know, these are descriptive only, site investigation requirements, environment, handling, storage, quality control, everything is there. So for this now, they have actually given us simple things now. The code has given you already that for temporary works now, the design life is 1 to 5. For short-term structures, 5 to 10 years. Industrial structures, 10 to 50. For long-term structures like highways and things like this, highway retaining structures are 120 years now. So we are designed for 120 years means what? In considering our long-term design strength actually, we have taken into account 120 years of creep also apart from other things now. Okay, 120 years of any damage is going to occur due to environment now, due to wrong burial, due to exposure. So whatever factors are going to consider will be this now. So mind you, what we are trying to look at very cutly and quickly, if you are going to have the creep as a criteria, which is there of course, so a material which is going to have 100 kilonewton per meter strength will have all these factors, and let us say we are going to allow only 50% of it. So that means the actual strength which are going to use will be 50 kilonewton per meter only. Whereas the creep is going to be much less, 1 to 5, 1 years to 5 years. So probably we will use 80% of the strength now. That means the design strength we are going to get is much more than what we are going for 120 years life. That is important. In other cases, like vessel reinforcement, we find that structure is permanent structure. But then we know that the life of the structure is like 100 years now. But we know that the consolidation will occur in 5 years, in 10 years now. So that means the loads which are going to the reinforcement has to be borne by the geosynthetics only for 10 years now. After that now, the soil is consolidating, gets its own strength now. So actually the geosynthetics is redundant now. In which case, what we are going to do now? We are going to apply less factor of safety. That means we are able to give more allowable strength actually. So that is why design life is important, which is not the normal concrete structures. You know, the concrete method, we don't consider this, it's just assumed certain values now. And so these factors we'll discuss in great detail next class. But one more point which you have to remember is going to be, which is very unique for this code of practices, is a partial factor of safety for economic ramification of failure factor. It's very important for us because when a failure is going to occur, how critical is the loss now? For example, if you got high abutment or high bridges and things like this now, structures directly supporting motorways, trunk roads, principal roads, railways, inhabited buildings, dams, walls, etc., all of them are considered as critical. So they have high ramification failure. So the factor is going to be 1.1. The factor is going to be used for every other factor of safety. That is very important now. For other things now, obviously, low and medium, the factor is only 1. That means we are not going to multiply by this factor of ramification. Only here, if something failing, the structure is failing now, naturally we have to take additional precaution. So not only the height and other parameters now, we got additional factor when we are constructing these kind of structures now. And what structures are going to be giving what now? We'll see probably next class. It will define actually what are those category 1, cat 1, cat 2, cat 3. That means low ramification, mid ramification, high ramification is defined very clearly. These pictures I will discuss next class, that is tomorrow, and understand why they are saying all things now. Okay. So that's why, as I said, is illustrative very clearly. And same thing is going to happen with the factor of safety for material also. They consider during manufacture, during construction, during long-term usage now. So all of them are combined into certain factors, and that's why I said it is a lesson by itself actually. That is way we gave a background of all of them in the earlier class, and now we are trying to look at now how to adopt it, because this is numbers now, and how these numbers are arrived at also is made very clear by this code. So we'll continue in the tomorrow's class. But then, if you got any quick doubts, you are welcome to ask me. Okay, we'll continue tomorrow then and see maybe the load combinations and then go further. Thank you then. See you tomorrow.